Have you ever really looked at that little blue dot on your phone and just wondered, how? How does it know exactly where you are on this planet of ours? I mean, the Earth isn't some perfect marble, right? It's lumpy, it's bumpy, and it's always shifting around. So today, we're going to pull back the curtain on the incredible science that takes our messy, real world and turns it into those clean, perfect grids we call maps. All right, let's kick things off with a question I bet you've run into. You're looking at your GPS and it says you're right on the money. But then you look at the map on the screen and it shows you're kind of off the road. Or maybe a property line just looks a little skewed. So if our GPS is so darn precise, why does this happen? Well, to get to the bottom of it, we have to go on a pretty fascinating journey. So, step one, we've got to deal with the Earth itself. It's not a perfect sphere. Not even close. It actually bulges out at the equator and gets a little squished at the poles. And that's before you even think about mountains and deep ocean trenches. To do any kind of real math, we can't use that messy shape. We need a simplified, totally predictable model to work with. And that model is the ellipsoid. Here's a good way to think about it. Imagine the real Earth is a lumpy, kind of irregular grapefruit. An ellipsoid is like a perfectly smooth, machine-made orange that we use to represent it. No, it's not a perfect one-to-one match, but it's a beautifully simple and mathematically clean shape that we can use for all our calculations. It's our ideal Earth. But here's where it gets really interesting. Not all ellipsoids are created equal. The WGS84 ellipsoid, that's the one your GPS uses, is designed to be a best fit for the entire planet. But for more local mapping, say in peninsular Malaysia, a different ellipsoid like the modified Everest actually fits that specific curve of the Earth much better. Just look at the difference in the radius. It's almost a whole kilometer. These small differences are a huge reason why a global system and a local map might not line up perfectly.
Okay, so we've picked out our perfect orange, our ellipsoid. But now what? We can't just have it floating around in space. We have to somehow fix it in place, to pin it to the real, lumpy grapefruit Earth. It needs a solid reference point. It's got to be anchored.
And that's where something called a geodetic datum comes in. If the ellipsoid is our orange, the datum is like the skewer we stick right through it. It defines the exact center of our model and which way its axis is pointing. It effectively pins our mathematical orange to a specific spot on the real Earth. This is so important. Every single coordinate you ever see is based on a specific datum. And this is a perfect real-world example of how that works. You can see that Malaysia has historically used different datums for the peninsula and for East Malaysia. Then they adopted a national one, GDM 2000, and of course you've got the global WGS84 for GPS. That's 4 different reference systems, 4 different skewers for the very same piece of land. All right, so our model is chosen and it's anchored in place. Now we actually need a way to describe a location on that model. We need a language, a way to define a single, precise point. And we really have 2 main languages for this. The first one is geographic coordinates. You know this one: latitude, longitude, and height. The second is Cartesian coordinates. Think back to math class. It's just an X, Y, Z system that starts from the dead center of our ellipsoid. It's maybe less intuitive for us to look at, but for computers doing heavy-duty calculations, it's incredibly powerful. Now, it's really important to get this. We can switch between these 2 languages. That's called a coordinate conversion. We can take a latitude and longitude and translate it into an XYZ value. But the key, and this is a big one, is that this is all happening within the same datum. We haven't changed our fundamental reference system, we're just changing how we describe a point on it. And that brings us right to the heart of our original question. What happens when 2 different datums, 2 completely different reference systems, collide? What happens when your GPS, which speaks the language of the global WGS84 datum, tries to talk to an old local map that was built on, say, the MRT68 data? Okay, so we have to get this one thing straight because it's crucial. We just talked about conversion, right? That's just switching formats. But to make 2 different datums line up, we need something way more complex. We need a datum transformation. This isn't just changing the language, it's changing the entire dictionary. We're shifting the fundamental reference frame. A datum transformation is basically the mathematical magic that lets these different map systems talk to each other. It's how we can take a coordinate from a brand new GPS and place it with incredible accuracy onto a map that was made decades ago using a totally different starting point. So how do we do it? Well, the most common way is called the 7-parameter transformation. Now, don't worry about the math, just picture this. You're basically taking one entire 3D grid, and you are physically shifting it, you're rotating it, and you're even resizing it just a tiny bit until it fits perfectly on top of the other one. It's those 7 little tweaks that line up 2 completely different views of the world.
We are on the home stretch now. We've got our coordinates, they're on the right anchored model, and we've even transformed them if we needed to. But we still have a location in 3D. So our final step is to solve the oldest problem in mapmaking. How in the world do you put a round Earth onto a flat screen or piece of paper?
You do it with a map projection. Seriously, think about peeling an orange. There is absolutely no way to flatten that peel without stretching it or tearing it or distorting it somehow. A map projection is just a fancy mathematical formula that decides exactly how we're going to stretch and distort our 3D ellipsoid to get it to lay flat. And this brings us to what might be the fundamental truth of all mapmaking. It's a key takeaway from the source material, and it's this: you can't have it all. Every single flat map is a compromise. You have to choose what's most important for your map's purpose. Do you want to preserve the true shape of continents? Okay, but then you have to distort their area. That's why Greenland looks absolutely gigantic on a standard Mercator map. Want to preserve true area? Fine, but then you're going to have to give up true shapes. Every flat map you have ever seen is, in its own way, a beautiful and necessary lie. And that's exactly why we have so many different types of projections. Whether it's the old Cassini-Soldner for local maps or the transverse Mercator that's used for the huge UTM grid system, each one is a different tool for a different job, and each one comes with its own unique set of strengths and its own unavoidable distortions. And that brings us all the way back to the beginning. The reason your GPS dot might not line up perfectly with a map isn't because one of them is wrong. It's because they might be using different ellipsoids, anchored by different datums, and then flattened using totally different projections. Every map is this intricate system of carefully chosen models and compromises, all designed to give us a useful but always imperfect view of our world. Which leaves us with one last thing to think about. We now have amazing tools like Google Earth that let us fly around a 3D model of our planet. So in a world with that kind of tech, is there still a place for the compromised, distorted, good old-fashioned flat map? What do you think? It's something to ponder the next time you ask your phone for directions. Thanks for joining me.